9.9, exceptions to the octet rule. So far, we've been building all our Lewis structures based on the octet rule, trying to get atoms up to have 8 electrons around it. We're going to find out there's exceptions to this. First up, we have incomplete octet. And these tend to be the smaller atoms that can't hold 8 electrons around such a small nucleus, such a small nuclear charge. We've already seen one with hydrogen. It only wants 2 electrons. Beryllium. Sometimes beryllium will form more ionic compounds. When it forms more covalently charactered compounds, it only wants to have 4 electrons. It only wants to form 2 bonds. Boron and aluminum, they're a little bit bigger. They like to have 6 electrons around them or form 3 bonds. All right, so let's look at BF3, boron trifluoride. It says draw resonance structures and assign formal charges to predict the most plausible structure. I've already done the skeletal structure here. Boron has 3 valence electrons. Fluorine has 7, and there's 3 of them. All right, so that's 21 plus our 3 is 24 valence electrons. I've already written out 6, 2 for each of the bonds. So now we're down to 18 electrons. So what I'm going to do is fill up my fluorines by putting 6 electrons around each. As I can see, when I'm done, my boron is only going to have 3 bonds around it. So what I can do, just like we've been doing, is I'm going to choose one of the fluorines, and I'm going to end up making a double bond with one of those. All right, I'll take a bond, move it in here. Now I have a double bond. All right, assign formal charge. Let's do that quickly. So we have 2 fluorines that are the same. One on the top and the one on the lower right, because there's 7 valence electrons, there's 6 lone electrons, minus 1 bond. They're both 0. The boron in the middle, all right, 3 valence electrons, minus 0 lone, minus 4 bonds, minus 1. The fluorine in the lower left, the one with the double bond, 7 valence electrons, minus the 2 lone pairs, that's 4 electrons, minus 2 bonds, plus 1. All right, so those numbers aren't great. The -1 is on the boron. The fluorine, which we know is the most electronegative atom, has a positive charge. That's very rare. Is there a way that we can do this better? How about we just leave it as an incomplete octet? And let's look at the numbers for that one. So if I just fill this up like we just had, all right, just those 6 electrons around there. And now I can do my same Lewis structures here with the formal charge. All the fluorines now are the same bonded, right? There's 7 valence electrons minus the 6 lone electrons minus the 1 bonded pair. They're all going to be 0. Boron in the middle, 3 valence electrons minus no lone electrons minus 3 bonds, 0. So by not forming a double bond, by not forming an octet for the central atom, I ended up with 0s for all my formal charges. All right. If we want to draw all these out, I could draw them out like this as well. All right. But if they said, what's the most plausible structure? This first one. All right, the other ones are legal. They're fine. All right, they follow the octet rule, but we're going one step beyond the octet rule here, looking at the formal charges. And the formal charge say this would be the most plausible one. The one with all single bonds, the one with the incomplete octet. Next up, we have odd electron molecules. These tend to be very reactive because of that having that odd number of electrons. All right, it says draw nitrogen dioxide, resonance structures if applicable, and assign formal charge. Here's the skeleton structure. How many electrons do I have? All right, my nitrogen is 5. My oxygen, there's 2 of them there. All right, so that's going to be 12, 6 each. So I'm going to have a total of 17 electrons to place. I've already placed 4, so now I'm down to 13 electrons. We've said let's fill up the ones on the outside first. So 13, I'm going to put 6 around each of the oxygens. But then I'm still left with 1 electron. I'll just make it a dot above the end. All right, so the oxygens have 8 electrons. The nitrogen only has 5 electrons right now. Let's at least make 1 double bond. Let's move this guy over here. Form that double bond. Now let's do formal charge. Here, the oxygen on the right-hand side, I'm sorry, the left-hand side, has 6 valence electrons to start, minus 4 electrons unbonded, minus 2 bonds is 0. The nitrogen in the middle, 5 valence electrons, minus 1 electron around it, minus 3 bonds, equals plus 1. And the outside nitrogen there, oxygen there, 6 valence electrons, minus 6, minus 1, have a negative 1 overall value. So again, this is a possibility. All right, we could have the same, it says draw resonance structures. I would draw the same thing, but instead of having the double bond between the first oxygen and the nitrogen, it would be the second oxygen and the nitrogen. We have incomplete octet. We also have expanded octet. Expanded octet means we have more than 8 electrons around that central atom. A good example here is our arsenic pentafluoride. Arsenic is in group 5, so it has 5 valence electrons. We have the 5 fluorides, which have 7. So we end up with 40 total valence electrons. All right, and we've already placed 10. So I have 30 left to place. And that divides nicely around my fluorines, right? I put 6 around each one. I'm not going to do all 6 just for time, but you know what it's going to look like. And they're all going to be bonded the same. And when I do formal charge, my arsenic in the middle, 5 valence electrons, minus 0 lone, minus 5 bonds, 0 each fluorine. 7 minus 6 minus 1, also 0. All right. A very important part of this is that only larger atoms can have this. So only elements, phosphorus and large. We find phosphorus in the middle of period 3. Only that and bigger can have an expanded octet. So our carbon, nitrogen, oxygen, fluorine, they cannot have an expanded octet. They're too small. All right, last example here. Let's try SF4. All right, count valence electrons. Sulfur has 6. Fluorine has 7. All right, 7 times 4, we get 28. 34 total. I've already used 8, so I have 26 left to place. So I'm going to put 6 around each fluorine. That's 6 times, there's 4 fluorines, so that's 24. So I'm going to have 2 electrons left. Where am I going to have to put them? I'm going to have to put them on the central sulfur. Even though it looks full, right? I have those 2 electrons left to place. I can't put them on the fluorines. The fluorines are too small to have an expanded octet. But the sulfur, bigger than phosphorus, is going to be able to have a lone pair of electrons just kind of stuck right there in the middle. When I look at formal charge, My sulfur has 6 valence electrons to start. Minus the 2 of the lone pair, minus the 4 bonds is 0. Fluorine, 7 minus 6 minus 1, also 0. So again, this is the most likely structure for it. One more quick example, xenon difluoride. All right, here we have xenon, a noble gas, bonding with fluorine. We can get this under extreme conditions. Counting out valence electrons, xenon has 8. Each fluorine has 7. So we're going to have 22 total. I've already placed 4. So we have 18 left to place. We know we're going to place 6 around each of the fluorines. So that's 12 total. That leaves me with a total of 6 more that I have to place. Where am I going to put them? I'm going to put them on the xenon. And let's look at formal charge to see if that was a good idea or not. Fluorine, we had this orientation for fluorine a bunch. 7 minus 6 minus 1 is 0. Xenon has 8 valence electrons, minus 6 unbonded electrons, minus 2 bonds, also equals 0. So this could be a plausible orientation.